affair. Okay. So if we look at the drawbacks of static CMOS logic that we just looked at, okay, static CMOS logic has a fan-in, with a fan-in of N requires two N devices. I need N PMOS and N NMOS. Okay, PMOS transistors consume a really large area, silicon real estate. So if you go back and look at the layout of PMOS, so here is a PMOS transistor, here is NMOS transistor. Okay, so PMOS transistors consume a lot of silicon real estate for two reasons. First reason is that each PMOS is sitting in its own well. Okay, for that reason, each PMOS transistors, the PMOS transistors have a large area. The second reason is that we typically like to have WP greater than the width of N, because mu P is less than mu N. In order to compensate, we have PMOS transistors that are much wider than NMOS transistors. So for these two reasons, the PMOS transistors consume a lot of silicon real estate. So if we can find a way to cut back on the number of PMOS transistors, that will reduce our the density of logic gates. That's another disadvantage. The first disadvantage is that we need a lot of transistors. The second one is that PMOS transistors consume a lot of area. Also, the propagation delay increases quadratically as the function of the fan-in. In other words, TPD raising, TPD falling, they increase rapidly as the number of inputs, okay, N, number of inputs increases. As a matter of fact, they increase as the square of the number of inputs. Okay, so that's the idea of, that's the disadvantage. The propagation delay deteriorates quite rapidly. Okay, so if you look at the graph, on the x-axis, there is the number of inputs. As the number of inputs increases, look at what happens to the delay of the propagation delay of a two-input NAND gate, of a NAND gate. Okay, the TPD falling. Okay, that is TPD high to low. Okay, that increases as a squared in a quadratic, and TPD rising, which is the same as TPD low to high, or TP low to high, increases linearly for a NAND gate. Okay, for the NOR gate, the opposite is true. For the NOR gate, PMOS transistors pull-up network is in the series. Therefore, this quantity increases rapidly, and this quantity increases a bit more in a linear fashion. Okay, but the idea is, as the number of inputs increases, the delay increases as well. So that's a disadvantage. So in order to fix all of these problems, we use what is known as dynamic logic gates. Okay, so dynamic logic gates is, in some sense, a solution to all the problems of CMOS logic. This CMOS, we are going to refer to that as static. Okay, dynamic logic gates are an improvement or a modification of static CMOS logic. Let us see the basic principles of static CMOS logic. It is used, the basic principles of dynamic logic. Dynamic logic is used to reduce the complexity and increase the speed and reduce the area compared to static CMOS logic. Okay. And that is achieved by lowering the number of PMOS transistors. Okay, we want to get rid of as many PMOS transistors as possible, and that is exactly what we do in dynamic logic. Okay, pull down network is exactly the same as in the static CMOS logic. Okay, but I want you to pay attention to two terms here. The idea of dynamic logic, okay, the idea of dynamic logic fundamentally comes from a capacitance, okay, a temporary storage using a capacitance and then a clock. So all of these together, okay, that contributes to dynamic. Okay, what is the characteristic of dynamic logic circuits? The characteristic of dynamic logic circuits is that a capacitance is used, a clock is used, and then a temporary storage of charge and capacitance is um, the operating principle. Okay, so that is what makes the dynamic circuits dynamic. So without further ado, let's look at the circuit for a typical dynamic logic circuit. Okay, a typical dynamic logic circuit. So let's do this. I'm going to, let's see, add a page. I'm going to do this for the sake of comparison. Let's look at the dynamic logic circuit and the static logic circuit in um, next to each other. So this is the dynamic logic, right? Okay, let's look at the static logic, which is this guy. Okay, okay, we'll use this guy, oops, and then see how they are different. No, just give me 1 second so I can copy this and get going. Let's see. Okay, let's put them right next to each other, the dynamic logic gates and the static CMOS logic gate, and then compare them. So this is static CMOS. This is dynamic. Okay, we'll quickly compare them to see similarities and differences. Okay, good. Now, if you see, the pull down network is exactly the same. The pull down network is exactly the same in CMOS logic and dynamic logic gates. Okay, so that's there. And then there is, of course, the power supply and then the ground, the lower power supply. Now, what is different is the pull up network of static CMOS logic is replaced with one PMOS transistor. Okay, one PMOS transistor. In addition, there is also one NMOS transistor down below. Okay, so that is different. And in addition to that, there is SC load capacitance. So that is different. And if you notice, these PMOS and the NMOS here are driven by the same clock input. Okay, so it's easy to see that there is quite a bit of similarity between the static CMOS and the dynamic CMOS, but then there is also some differences that are significant. Okay, the main differences are that the dynamic CMOS has only pull down network, and then there is one PMOS and one NMOS, and then there is the CL capacitor, and then of course the clock input. Okay, and I mentioned that these together, okay, the CL, load capacitance, clock, and the temporary storage together, they constitute the basic dynamic operation. Okay, questions please. Questions so far. Okay, the dynamic, yeah. So it seems
chat. Okay.
The question is, will the video lecture be available on YouTube? Yes, later tonight I'll post it on YouTube. Okay, other questions please. So dynamic CMOS is a spin on static CMOS. We reduce the number of PMOS transistors. That way we are consuming much less silicon real estate, and we are also contributing much less capacitance, thereby operating at a higher speed. Okay, so that's the dynamic logic circuit. Okay, so a single clock is driving a complementary pair of PMOS and NMOS. Okay, this guy is also called the foot transistor. Okay, NMOS logic network acts as a composite switch. So like I mentioned earlier, so this switch is still intact. The pull-down network is still intact. Okay, the pull-up network is not present. Okay, the pull-up network is not present, but this pull-down network still acts as a switch. Okay, now another important point about dynamic logic circuit is that it is temporary, or the output is valid only for a short period of time. Okay, and I'll show you why that is the case in a minute. Okay, so the output is valid only for a short period of time. Okay, let's see. There are two modes of operation. There are two paradigms of operation for dynamic logic gate. Okay, shown in red is called the precharge phase, and that happens when the clock is 0. Okay, when the clock is 0, we are in precharge phase. Shown in green, the evaluate phase happens when the clock is 1. Okay, the evaluate phase happens when the clock is 1. Okay, the output is valid only during the evaluate phase. Okay, pre-charge, the output is not valid. Evaluate, output is valid. Okay, output is valid. Okay, that's the idea. If I wanted to implement something like this, A times B plus C, A and B NMOS transistors are put in series, and C, the PMOS, the addition transistor, that is put in parallel because it is adding. Okay, so the logic is still the same. Okay, the logic is still the same. The way the PMOS and the way the NMOS transistors are connected in series and parallel, that is still the same. The only thing that is different is that the pull-up network is being removed. Okay, when the clock is 0, I have a pre-charge phase. Okay, when the clock is 0, there is the pre-charge phase. When the clock is 1, there is the evaluate phase, and I will show you how they operate shortly. Okay, pre-charge phase when the clock is 0, evaluate phase when the clock is 1. So during the pre-charge phase, the output is not valid. Output not valid during the pre-charge phase. Okay, so this is preparatory stage. This is preparation stage. Okay, even before the logic is evaluated. So let's see how it operates. Pre-charge phase happens when the clock is 1. The clock is 1, or the clock is 0, right? When the clock is 0, the same value of 0 appears on the gate of the MP and ME. But because the clock is 0, the PMOS transistor is on and the NMOS transistor is off. NMOS transistor is off. Okay, the NMOS transistor is off. Okay, so this is floating. There is no connection now available to the ground. So the only connection available is from VDD, the power supply, to the load capacitance here. So in pre-charge phase, the load capacitance takes a value of VDD, or it is fully charged to a value of logic 1. Okay. During the pre-charge phase, all the load capacitances are connected to the power supply. Okay, and then they take a value of logic 1. Okay. Now that's the idea of pre-charge phase. Now evaluate phase comes next. During the evaluate phase, the output is valid. And the output is valid only during the evaluate phase. And that happens when the value of the clock is 1. The value of the clock is 1. So the gates of both PMOS, MP, and the NMOS, ME, both of these values are 1. So what happens is, because the value on the gate is 1, that NMOS connects to ground. And guess what happens to the PMOS on the top? That is going to be off. Okay, so there is no connection to the power supply. Okay, there is no connection to the power supply. The only, or the VDD power supply, the only connection is from this switch pull down network. I know this is a switch, right? I know from this switch, okay, to ground. Meaning, if this switch is on, then CL is going to be connected to logic 0. Okay, and if this switch is off, if pull down network is on, then the load capacitance is going to see a value of logic 0. If the pull down network is off, then load capacitance should be at the value of VDD. Remember, earlier during the pre-charge phase, this was charged to VDD, okay? Because pre-charge comes before evaluate phase, okay? Remember, I charged it to VDD. I charged that node to VDD, okay? By following the pre-charge phase, okay, this capacitance has a value of VDD, okay? Now the evaluate phase comes. During the evaluate phase, either this pull down network is on or off. If the pull down network is off, then there is no connection between the output, because the pull down network is off. There is no connection from the output node, okay, from that node. There is no connection from the output node, that guy, okay, to ground. So the VDD will remain the same. On the other hand, if the pull down network is on, okay, if this composite switch is on, then the output will be driven down to ground. Okay, so this is how the logic is implemented. So the output is only valid during the evaluate phase. Does that make sense? Questions, please. Okay, so let me summarize the idea here. Pre-charge and evaluate phase summary. Dynamic logic circuits. They have only pull down network, okay, plus one PMOS plus one NMOS. This NMOS is also called the foot, okay, and then it also has a clock, comma, load capacitance, okay, load capacitance. When the clock value is 0, I'm in pre-charge phase, okay, I'm in the pre-charge phase, and then in the pre-charge phase, the output not valid, okay, and as a matter of fact, all outputs, they are charged to VDD or logic 1, okay, that's the idea. During the evaluate phase, when the clock is 1, we have evaluate phase, okay, the output is valid here. There can be two conditions. If the pull down network is on, then the output is going to be logic 0 because it is going to be connected to ground. If the pull down network is off, then the output should remain at VDD or logic 1. Okay, the output, the load capacitance, there is no discharge path for the load capacitance. So it does not discharge, the capacitance should hold its value. Okay, questions please, questions so far. Okay, so let's look at the summary and properties of dynamic logic gates. Okay, the logic function is implemented by pull down network only. There is only pull down network. The total number of transistors is n plus 2. If the number of inputs is n, then the static CMOS uses 2 times n, while the dynamic uses fewer transistors. Okay, the dynamic uses only n plus 2 transistors. Okay, and there is full swing outputs all the way from ground to VDD, and then there is faster switching speeds because the PMOS transistors are absent. A lot of load capacitance is absent. In addition to that, there is no short circuit current. Our static CMOS had a problem. For a short duration of time, okay, for a short duration of time, both the PMOS and NMOS were active, were on in saturation, thereby providing a path from VDD to ground. The blip of current, short circuit current, that happens in static CMOS is not present in dynamic CMOS circuits. Okay, so the short circuit consumption is not present in dynamic logic circuits. Okay, let's look at the idea of evaluate. As a matter of fact, we did look at the idea of dynamic logic gates, right? Dynamic evaluate phase. During the evaluate phase, clock is 1. Okay, therefore MP is off, the bottom transistor is on. Okay, the bottom transistor is on. So this is exactly what we discussed just now. This guy is going to be on. Okay, this guy is going to be on, and based on if this switch is on or not, okay, based on that, um, the output is going to be either logic 1 or logic 0. Okay, that is when the inputs, the logic inputs that are applied, they evaluate the circuit. Okay, now what do you think could be the issues in dynamic logic gate? What do you think could be the issues in dynamic logic circuits? There's no free lunch, right? So by reducing the number of PMOS transistors, what cost am I paying? Any volunteers? Okay, so the problem typically comes from this capacitance here. Okay, the problem in dynamic logic gates always comes from the dependence on capacitance. Okay, so let's go back to the dynamic logic gates review here. I mentioned that the output capacitance CL is charged to VDD during pre-charge, and then it's left floating. Okay, it's left floating. So that is a big problem. The idea that a capacitance is used to store a charge gives rise to the situation where the capacitance is leaky. Okay, always what happens is when I am storing charge on a capacitance, capacitances always tend to find some leakage path to lose their charge. Okay, so let me list the problems in dynamic logic circuits. Okay, there are 4 problems in dynamic logic circuits. Okay, dynamic logic circuit typically has a PMOS, okay, and a pull down network and one NMOS. Okay, the PMOS and NMOS are connected to the same clock. Okay, the output here is connected to the load capacitance CL. Okay, that's the idea of a dynamic logic gate, right? So this capacitance here, when I charge it to VDD during the pre-charge phase, there can be a bunch of different problems after that. The capacitance, if you leave it with a charge of VDD, it should hold that value ideally. But then what happens is the capacitance leaks some charge. Okay, and in addition, there is also some charge shading. Okay, the capacitance here, it shares some of the charge with other parasitic capacitance somewhere else. Okay, and then there is this capacitance, the CL, also acts as an antenna, and it receives a lot of um, noise, environmental noise. Okay, the capacitance receives a lot of environmental noise. And we also know about clock feed through, right? We will revisit the idea of clock feed through. Clock feed through, if you remember, when we were doing transmission gates, before doing transmission gates, we were talking about pass transistors, gate, drain. The problem with pass transistors is this overlap capacitance between the gate and drain. That guy, okay, this overlap capacitance, that shorts the clock to the output at high frequencies. That's the idea of clock feed through. And that's exactly the same problem showing up here as well. Okay, and that is showing up on this PMOS transistor. The clock, okay, is going to feed from the gate to the output. Okay, that's the idea of clock feed through. So some of these problems we already know. We know the clock feed through problem from the past transistor logic. Capacitive coupling happens because capacitance acts as an antenna and picks up a lot of environmental noise. Okay, backgate coupling, there are a lot of problems. So let's look at the charge leakage mechanism. There's the charge here that's supposed to be VDD. After pre-charge, it keeps leaking. Okay, so let's look at that problem. Okay, so pull down network is off. Let's say the pull down network is off. Okay, let me say the pull down network is off. And I'm going to show that by, if you notice, the value of A is 0 over there. Okay, the value of A is 0. So therefore, this NMOS transistor is off. The NMOS transistor right there, M1, that NMOS transistor is off. So there is no connection between the load capacitance and ground. Okay, there is no connection between the load capacitance and ground when the A value is 0. Okay, so ideally, if I put a value of VDD on the load capacitance here, because there is no path to ground, it should hold its value. There is no path to ground. It should hold its value. But what happens is, even though there is no direct path through the logic gate, so there is no direct path this way, that path is absent. But what happens is there are some leakage paths. There is some other path from here to ground. There is more than one path from here to ground. There are different kinds of transistor leakage mechanisms that bypass this path. This is the main signal path. This signal path is bypassed, and then even though this is off, the capacitance loses its charge through many other leakage paths. That's the idea. So what happens is, this is what happens, okay? Let's say during the pre-charge phase, that is when, this is the pre-charge phase, right? The clock is 0, so this is all pre-charge phase. When the clock is 1, this is all evaluate phase. This is all pre-charge phase, okay? When I pre-charge the load capacitance, this guy, to 1 and leave it there, ideally, it should hold its value if this NMOS transistor is off. If the NMOS transistor is off, the capacitance should hold its value at VDD. But even though this NMOS transistor is off, there are other paths, there are other problematic paths that leak the charge from the load capacitance here. Okay, then what happens is, instead of staying at 1, the voltage on this capacitor keeps falling continuously. Okay, so think of this as being similar to a leaky bucket. Okay, think of this as being similar to a leaky bucket. Let's say you fill the bucket with water. Okay, you fill the bucket with water, but if the bucket has some holes in it, it's eventually going to empty. You would expect that this bucket should be full with a logic 1, but because of these leakages, okay, the water is going to drain out and it is going to tend towards a logic 0. Okay, so in other words, what you have to do is, if you have to carry water from point A to point B, you have to make it fast. Okay, you have to operate at a really high frequency or at a really slow, at a really small time. You should really, if you want to take this bucket of water from point A to point B, if you are slow, the bucket is going to end up with no charge, no water. Okay, but if you are fast enough, okay, there is still going to be some amount of water left by the time you reach point B. Okay, so that is pretty similar. The idea is you have to be very fast. You have to operate at a high frequency. If your frequency is low, then your output logic will approach zero. So in other words, there is a lower limit on the F clock. If you operate any lower than that prescribed value, then your circuit malfunctions. Okay, pretty similar to if you are slow in carrying a leaky bucket, then you will not be left with any water. Even so, if you are operating at a slow frequency, then the leakage mechanisms drain the voltage on CL towards ground. So if you're fast enough, if you're fast, what happens is this one, where it's supposed to be there, it's still reasonably close enough. Okay, that's the idea. So charge leakage, there are four sources of charge leakage. Charge leakage imposes a lower limit on the frequency of operation. Okay. Okay. Now, charge leakage imposes a lower limit on the operating frequency. Okay, that's the idea of charge leakage. Okay, let's look at another problem, the idea of charge shading. Okay, let's say I have a logic, a two input logic where A is 1 and B is 0. Okay, because B is 0, let's pay careful attention. The, the transistor B is going to be off. Okay, because the transistor B is off, it's not going to, the output is not connected to ground. Okay, so let's say we are going from a pre-charge phase. Let's say the clock is initially 0, clock is 0. Okay, when the clock is 0, this capacitance reaches a value of VDD. Okay, that's the pre-charge phase. Then the clock becomes 1. When the clock becomes 1, what happens is we are in the evaluate phase. In the evaluate phase, the value of A is 1, B is 0. So there is going to be a connection between power supply, between the output to this node here. But because B is 0, this connection does not continue to ground. Okay, so in this condition, the output capacitance should hold its value at VDD. Okay, so if you think of this output capacitance as a bucket, CL, it is full of water. Okay, this bucket is full of water, and let's ignore the holes in that for the minute. Okay, but now it is not connected to ground, but look what is happening here. There is an empty bucket here in the form of CA, this guy. Okay, when this guy is empty and then a connection is established because of A being 1, a connection is made from CL to CA, then what happens is CA receives some of the water from this load capacitance and the load capacitance itself is going to lose some of its water. Okay, so in other words, what happens is even though the output is supposed to be at VDD, even though the output is supposed to be at VDD, because of this connection to CA, okay, some of the charge is shared with the capacitance here, and VDD is going to, or the output is going to be less than VDD, okay, less than VDD, just like the water level has dropped here by connecting it to an empty bucket. What happens is the output value falls below the VDD. Fortunately, there's an easy fix to that. What we do is we employ the technique of pre-charging. Okay, so what is happening is during the pre-charge phase, this critical node, which has a parasitic capacitance CA, okay, and then the load capacitance is CL over here. So during the pre-charge phase, what we do is we charge this capacitance to this node and this capacitance to VDD as well. So this node is charged to VDD and this node is charged to VDD as well. So what happens is this is similar to connecting two buckets, okay, both of which are full with water. Okay, now what happens is when I'm doing this, when I'm making a connection between these two nodes, this is CL and this is CA. When this connection is made between these two nodes, there is no water flow in any direction. That way, the VDD that is supposed to be here is not, um, the charge there is not shared with this guy. Okay, so let me rephrase that. By pre-charging critical nodes, what I am doing is I am not sharing the charge here to eliminate the problem of charge sharing. Okay, that's the idea of charge sharing. So in addition, if we were in the class, we would have done an analogy of a balloon, a full balloon, a deflated balloon, and a full balloon, and then some holes in the balloon to represent the charge leakage, so on and so forth. Okay, but these are the problems in dynamic logic circuits. The idea is the capacitance, the load capacitance over here that leads to a lot of problems. We rely on this capacitance holding the value at VDD, but there are some leakage mechanisms, there is some charge sharing, and there's also a lot of crosstalk. Okay, any big swing on the output capacitance here is going to be coupled into this guy. Okay, there is going to be a lot of susceptibility to uh, environmental noise. Okay, and then of course there is clock feed through. As I mentioned earlier, the clock that is here feeds into the output through the overlap capacitance there. Okay, and that's the idea of clock feed through. Okay, and then these are all the problems because of clock feed through. What is supposed to be a 1 goes over 1. Okay, the output that is supposed to be 1 goes beyond VDD because of clock feed through, so on and so forth. Okay, so these are the issues in dynamic logic circuit. So let's quickly summarize. Dynamic logic is based on the storage of charge on a capacitance, okay, on the load capacitance. Sure enough, um, we know that very well because it gives us a lot of problems, okay? And in addition to that, there is a two-phase scheme. There is a pre-charge phase where all outputs are charged to VDD. The output is not valid. And then there is an evaluation phase. This is where the output is valid. Depending on the logic, the output is either 1 or a 0. Okay, and then it is very fast. It consumes very low, much lower area power consumption. But then the dynamic logic circuits are very sensitive to leakage mechanisms, charge sharing, clock feed through, and environmental noise. Okay, so we can eliminate charge redistribution or charge sharing by pre-charging mechanism, pre-charge critical nodes, and um, we can reduce the effect of charge leakage by operating F clock greater than F clock minimum. By operating, by making sure that I'm fast, by my clock frequency is fast enough, by imposing a lower limit on the operating frequency, I can make sure that the effect of charge leakage is not adversely affecting my circuit. Okay, questions, please. What questions do you have? I'm going to upload this video later on tonight on YouTube. So make sure you budget enough time before the midterm. Look at the midterm posted on Canvas, and I'll see you folks back on Thursday. And the midterm does include all the material that we covered up until today. Okay?
Professor, I'm having a question.
Yes.
So in this logic, like in the dynamic logic, will the output be similar as the CMOS logic? Like if we have the two NMOS in series, so in CMOS logic, we get the output as A into B, right? So
Yes.
in dynamic logic also, the output be A into B, or it would be 0?
A times B whole complement, right? If
Yeah,
you have
sorry.
A and B in series, your
Mm-hmm.
CMOS logic will give you A times
A
B
dot B.
whole complement. Even so, the static CMOS logic also implements the exact same logical expression. Okay. As a matter of fact, let me go back a few slides. Okay. I'll show you the expression for logic gate. Okay. Right here. Okay. So I have one NMOS in series with another NMOS in parallel with an NMOS. So I have A times B plus C. That corresponds to the series and parallel combination. And the whole complement. Okay, that's exactly the same as a static CMOS, except that this is true only when the clock value is 1. When the clock value is 0, the output is always independent of whatever this logic is, independent of this logic. When the clock value is 0, the output is going to be 1. But when the clock logic is 1, I'm implementing the actual logic function. Does that make sense?
Yes, so it means that PMOS doesn't play a role over here. Only the PMOS, the role it plays is like it operates the clock over there.
Correct. This
Okay.
is the PMOS. And the rest, that's a very good question, actually. This is all implemented by the NMOS. The PMOS role is only to charge it to VDD.
So like the size of the whole circuit reduces to a large extent.
The size of the whole circuit is much smaller because the number of PMOS transistors is just 1. I'm not using N, the number of inputs, as the number of PMOS transistors. Does that make sense?
Yes.
Okay. Any other questions, please? All right. So all the material we covered up until today is going to be on the midterm. Good luck with your preparation. I'm going to be in my office hours on Thursday from 11 o'clock, so you can see me then if you need to. All right. So I'll see you folks back on Thursday.